stairwell opening calculation. So we're just going to do an example here of calculating a stairwell opening for a given building. I have a drawing to the right there. So we're going to use those dimensions. So I was going to write down some of those dimensions there. So the total rise is something that we would have to measure off of site. Total rise is the distance vertically from finished floor to finished floor. So for stuff that we do with homework here, I'm going to be giving you that number, but that would be a number that you'd have to measure on site if you're building a set of stairs or framing. So knowing the materials involved to then determine the total rise. For example, normally you measure from plywood to plywood if you're building a set of stairs. If we're doing the stairwell opening, you'd want to look at what's the length of your stud, what's the size of your floor joist. From there, look at strapping, drywall, what thickness of subfloor. Put all that together to determine your total rise prior to framing the floor. Okay, so you have to put all that together. So in our case, we're going to go with a total rise of 120 inches or 10 feet, which we can see on the drawing there off to the right there. Total rise from finished floor to finished floor. So in this case, we actually have already determined the stairwell opening, but it's going to kind of work through the math, not knowing that number. Okay, so that's what we're trying to achieve, is that 10'5". We're going to change this number slightly here. I'm going to make that 6'8" instead of 6'9.5". So that's probably going to change slightly. But I'd like to use this diagram to kind of help explain what's going on in the formulas to calculate the stairwell opening. So other information we have there is the floor system thickness, which is called upper construction, is 11.5 there. So that would have to be determined again off of the plan. So what's involved there would be basically strapping on the underside of the floor, drywall on the underside of the floor, the thickness of your floor joists, your subfloor, and then your finished product. So is it carpet, is it hardwood, is it half inch, is it 3/4, that kind of thing. So that's already been determined for us to be 11.5 inches. And in the headroom, like I was saying, code is 6'4" and 7/8", somewhere in that range there. We sometimes say 6'5". I'm going to bring that up to 6'8". So the headroom, we're going to go a little bit above code, and we're going to say that we want 6'8". I like to play around with 6'8", because interior doors are 6'8". So why not make the stairs 6'8"? Whatever I have to carry up the stairs is going to have to go through a bedroom door. So I kind of like to stick with that number. Okay, it's above code. We're not playing around with being at the bare minimum, which could cause a problem if we have issues with squareness and stuff like that. Okay, so the first thing I'm going to do there is I'm going to go ahead and I'm going to calculate the number of risers required for the set of stairs. Right, so to do that, I got to take the total rise of the stairs and then divide that by 7. So for residential stairs, we're aiming at basically having our unit rise be between 7 and 7 7/8. So that's why we use this divider here of 7. If we're looking at commercial stairs, we're trying to hit somewhere between 6 and 7. So we divide that by 6. And then for landscaping, we tend to hit somewhere between 5 inches. So we divide by 5. Okay, so this is residential inside of a house. So we're aiming for that range of 7 and 7/8 to get an ideal angle of between like 30 and 38 degrees. Okay, so the angle of the stairs, that's what we're aiming for. So if we use that number with a 10-inch run, we'll be in that range. Okay, so if we follow that through, we're going to take the 120 inches, which is our total rise, we're going to divide that by 7. Okay, so 120 divided by 7 gives us 17 point something. I'm not going to worry about the decimals. I'm just going to take that whole number for now and then see what I get for a unit rise. So step 2 there is getting my unit rise. Again, I want my unit rise to be between 7 and 7 7/8, which is code. Okay, that's the max. So I'm going to take the total rise now and then divide it by the number of risers, 17, right? So I basically have a set of stairs that from here to here is 120. I just determined that there's going to be 17 risers. So if I count them out, I'm not sure if this drawing is to scale, but let's just take a look. So 1, 2, 3, 4, 5, 6, 9, 10, 11, 12, 13, 14, 15, 16. So it's saying 16 there. So let's just see what we get with a number. We might have to change that to 16 if we're not hitting that range. So I'm going to go 120 divided by 17, which is going to give me an answer in inches. So 120 divided by 17, it gives me 7.06. So we could change that, or sorry, 588, which basically means we're at 7 and 1/16. Okay? So if I wanted to find the fraction rate, I just subtract the 7 out of the calculator, I'm left with all the decimals there, and I multiply that by 16 to find a numerator. So the numerator is 0, but if that's 5 or higher, I get round it to 1. So option 2 is maybe dividing it by 16 to make that number bigger. Right? So I'm just going to check option 2 here and see if maybe that's a better option. Okay? For more advanced thinking. So if I go 120 divided by 16, I end up with 7.5, which is not a bad number. It's probably where we want to be. All right, so option 2 is probably better. I think what I'm going to do just for first time through, I'm going to stick with the 7 and the 16th, okay, just so I don't play around. I know when I teach this in school, I normally say just take the whole number there and work through the math. When you get more experience, you can look at more than one option. In this case, I'd probably go with that one, okay? We'll just keep on going with the 7 and the 16th, so we're going to kind of avoid that, okay? So next thing there we're going to get is the unit run. So the unit run code has changed, right? So the unit run used to be from 8 1/4 to, I think, 14 and something. Now the minimum is 10 inches. Okay, so that has changed in the recent code revisions. But something that we've always kind of done is stuck with 10 inches. Right? Just make that a constant. So always, for what we're doing at school anyways, is stick with 10 inches. Reason being is material available to you. So when you go to a lumber yard and you try to buy a tread, you're probably going to get something close to about 11 1/4. Okay, so pretty well the max you can go for a unit run is 10, with a 1-inch nosing would give you about 11. So you might have to rip a little bit off that tread to make it work, but that's doable. So if we make that number any bigger than that, we're going to have trouble finding material to actually make those treads. So we could buy material, make our own treads, make our own nosings and all that kind of stuff, but that's a lot of work. A lot of stair parts are already made for us, so we're better off to see what we have available to us in the store and use that product. It's going to be cheaper, less delays, and in the long run, you're going to get the job done faster, right? No waiting times. But that can be bigger, right? That's basically the minimum. Step number 4 here is determining the total run. So the total run is the distance traveled horizontally of the stairs, right? So from that point to that point would be the total run. So basically what I have to look at is if I have 17 rises, that means I have 1 less tread, okay? So if we were to actually lay that out on a piece of paper, if I started from here, that's my upper floor, and I come down, that's 1 rise, that's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That's the bottom floor. So if there's 17 rises, including that one, then there's only 16 treads. There's always 1 less. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's kind of a rule, right? So if we want to determine the number of treads, we take the number of risers and minus 1. So number of risers is 17, minus 1 gives us 16. So we just prove that formula right here, okay? Number 5 might be getting our total run. Okay, so that was the first step to getting the total run. So we now know that there's 16 parts in that direction. Each of those parts is 10 inches. So that can help us get the formula, right? So if I have 16 parts, each part is 10 inches. So if I go 16 times 10, I got my total run. So basically we take the number of treads and multiply by the unit run. Okay, so it's all horizontal. Run, treads is horizontal, unit run is horizontal. So there's 16 treads multiplied by 10 inches gives us an answer in inches, which is 160, which is 13 foot, that's 156, so then there's 4 inches left over, 13 foot 4. So the distance from, if I drop the plumb bob, from that floor to the front of that riser without adding on for materials, would be 13'4". More than likely, we'll probably cap this off with a piece of veneer, whether it's oak or maple, and that'll buff the stairs over 3/4 of an inch. So that would shift that over a little bit. So it's good to know the total run, right? Because we might have a doorway at the bottom of the stairs. So we want to make sure that we have room here for finish on the stairs, finish molding on the door, and maybe a gap in between to show that there's no error there. We don't want those things all coming together and have to rip molding to make it smaller. That makes it look like there was an error there. Right? So knowing the total run, knowing where the stairs are going to end. So if this floor system was built, we're going to frame our interior walls, we could figure out where that total run is going to be, allow probably another 3 inches here, and then another probably 4 inches there, so 7 inches to the door frame to make sure that there's lots of room there for finishes. Okay. Number 6 there, we're probably getting the number of rises or runs in the opening. So number of rises / runs in the opening. So the stairwell opening. So that's where that picture to the right there comes into play. The formula for this is basically taking the headroom plus the upper construction, and then we divide that by the unit rise. So what we're trying to do is determine how many vertical parts are in the stairwell opening, and there'll be the same number of horizontal parts in that stairwell opening. Okay, so if you look at the drawing here, this is pretty well complete. Numbers are obviously a little off. We don't have the same number of rises. We don't have the same total run, right? So this has one less tread than what I'm using here, but it's still a good drawing to kind of look at. So you can see the formula right here. Number of rises or runs in the opening is headroom plus upper construction divided by unit rise. So what that's doing is looking at this distance from here to here, right? So that's headroom right to there, and then that's plus upper construction. So if we then take the unit rise and then divide that vertical distance, we then determine the number of vertical parts in the opening. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and a little bit. So it's 12.2 rises actually is what we ended up with when we did the math here. So if we have 12.2 rises, that means we have 12.2 runs, because there's the same number of runs as there is rises in the stairwell opening. I know we kind of just said the opposite of that, right? When we did this set of stairs, there's actually 17 rises. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. But there's only 16 treads. But in reality, if I were to bring that down and form a large triangle there, that would have to go all the way to the bottom here. So there's actually another tread there that we just don't buy because it's the floor. Right, but if we actually started from here, that big triangle goes all the way to the bottom. So there's actually same number of treads. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So there's 17 treads, but we only buy 16 because one of them is the floor. That's why we subtract the 1. So in reality, it's the same number, right? So whatever we have for vertical parts, we have the same amount of horizontal parts. So by knowing that, we just have to take the 12.2, multiply by the individual part size, which is 10 inches, and then that'll give us our stairwell opening. And then we normally add 3 inches for finish materials and for shimmy allowance. Okay? So if we kind of follow this through, the headroom is up here at 80 inches. Our upper construction is 11.5. And we're going to divide that by the 7 1/16. So something that I like to do, which is probably not the most crucial thing, but I like to use the number that's on the framing square for calculations. So 7.0625 would be 7 1/16. Right? So if I go 1 divided by 16, a decimal is exactly what I wrote there. So mathematically correct is this number, but we can't cut to that accuracy. We can cut to 7 1/16. When I actually set up my framing square to build the stairs, I'm going to set my framing square to 7 1/16 and 10. I'm going to mark out the piece of wood for the notches, right? So there's your piece of wood. These notches here are going to be 10, 7 1/16, 10, 7 1/16. So what I like to do is kind of ignore that number, which would be more accurate, definitely more accurate, but this is actually what we're going to have, 7 and 1/16. So let's use the 7 and 1/16 in our calculation so we actually get what we're going to build, okay? Slightly off, I agree, but what we're going to have, okay? So I'm going to divide this by 7.0625 here at the bottom. So I'm taking that number and I'm plugging it into that formula, okay? That's the one we use for calcs. Does it make a huge difference? Not really, but it's a little off. But this is what we're going to have. Remember that. That's what we're actually going to cut. So if we go through and do the math there, we'll go 80 plus 11.5 in brackets, press equals, and then I'm going to divide that by 7.0625. So I end up with 12.9557. So we've got to decide if we're going 2 decimals, which I probably will go. So I'll round that to 2 decimals. So if that's 5 or higher, I'm going to make that a 6, which it is in this case. So so it starts off by being 12.96 rises, which means there's also 12.96 runs. Okay? And then we got the last step there. I'm going to see if I can try and put that last step just at the bottom here so I don't lose the page. But so the last step there is getting the stairwell opening. So the formula for that is number of runs in the opening multiplied by the unit run, throw a bracket on that, and then plus 3 at the end. So the plus 3 is for extra material. So basically what we just determined is this section here, on our example, has 12.96 rises, which then means it also has 12.96 runs. Okay, so we're going to go basically the number of runs in the opening, which is 12.96, multiplied by 10 inches, and then we're going to add on 3 inches at the very end to allow for drywall here, allow for that riser board here, allow for the nosing on the treads, allow for shimming this header if it's not square, and then a little bit of room there for discrepancies in the building. So number of runs in the opening is 12.96 multiplied by 10 inches plus 3. So we're basically just shifting that decimal over 1, so it's 129.6 plus 3, so equal to 132.6. So we'll just put 132.6 here. Divide that by 12, so 11 feet exactly. Minus the 11 times 12, there'll be 0 inches there. And then times that by 16, which will give us, so 9/16, but that's 5 or higher, so we're going to call it 10/16, which is 5/8. Okay, so the stairwell opening is 11 foot 0 and 5/8, or if you want to write down 132 and 5/8 as finished product. So it's slightly different here, right? So it's a little bit larger, but we did go 1 tread more, right? So basically 10 inches more added on to that. Okay, so one last thing we might determine there is maybe the angle. So maybe I can just do that in this upper corner here, but if I wanted to find the angle, maybe to know what I have to set the saw to, so if I have the triangle that I would actually lay out my framing square to, so we have 7 and 1/16 here, and we have 10 here. So if I want to find this angle right here, okay, what I have to use is SOHCAHTOA. We use tangent, right? SOHCAHTOA is probably something you would have learned in elementary school or high school. The one we use the most with construction is TOA, which is basically the tangent, so inverse tangent of opposite over adjacent. So if we want to find this angle, the opposite of that angle is the 10. The adjacent of that angle is the 7 1/16. And this here is always your hypotenuse. So if I want to find this angle over here, that would be the opposite. This would be the adjacent. So it depends on what angle you're looking for. So if we're looking for that angle right there, we would then put it into the calculator that way. right? So tan of -1, opposite is 10, so the 10 goes on top, and then the adjacent goes on the bottom. And then I would enter that number into the calculator just like that. So I'd have to find the second function button, press the tan, then I see the tan of -1. Then I can open up my brackets and then go 10 divided by 7.0625, close the brackets, and then press equals. So I got to make sure my calculator is in degrees, otherwise this won't work. But then it gives me an answer there of 54.768 degrees. Okay, so what I can then do is also find the bottom angle by using logical angles. So if I have a right angle triangle, the sum of all three angles equals 180. So this is a right angle, so I already know that that's 90, which means that these two angles here have to equal 90. So if I know that that angle there is 54.768 degrees, if I just go 90 minus that angle, will give me that angle. Okay, and that's probably the one I'm actually going to use to set the saw to, is that smaller angle. So if I just go in my calculator, I'm going to get a negative number, but just for speed there, if I go minus 90, it gives me 35.23 degrees. So if I want to cut that angle on a saw, I'd actually have to set the saw to 35.23, and it would give me a 54.76 degree angle. Okay, so it's a little bit confusing there, but if you've ever used a miter saw, right, whenever you're actually cutting a 90-degree cut on a miter saw, if you actually look at the miter saw, it's telling you you're cutting 0. So it's kind of the opposite angle, okay? Same thing with a speed square. If you grab a speed square and you actually try to mark out a 90-degree, it's telling you you're cutting a 0-degree angle. They're kind of set up the same way, which is opposite. So if we do the calculations and find the true angle of something, whenever we actually go to cut it, we have to cut the opposite because tools are set up that way. Okay, table saw is the same way, right? If you have the saw set at 90 degrees to the table, read the scale, it's telling you 0 degrees. So if we calculate that to be a true angle of 54, when I go to a saw to actually cut that angle, I cut it at 35.23. So where would I cut that angle? That angle could be part of the handrail, tying into a post. Right, so the angle that I would actually set the saw to would be 35.23. Where else would that angle might be? That could be the angle right here at the top of the stringer. Okay, will be cut at the 35.23. So a little confusing there, but that's kind of the way it works. I don't know, not sure the real logical reason for why miter saws are set at 0 when you're cutting a 90, but that's just the way it is, and we got to kind of go with it. So it's just a matter of realizing that, and if we calculate that angle correctly, we cut the opposite angle when we use the tools. Okay? Hopefully that helps out. If there's any questions, don't be shy to send them my way.